Hi, my name is Bob Cheesebrough, and I'm a technical consulting engineer in Intel's compiler team. Welcome to the first in a series of videos covering Intel compiler vectorization essentials. This series will focus on techniques a developer can use to utilize vector hardware to potentially improve application performance by using explicit vector programming methods such as found in OpenMP 4.0. Who is the intended audience for this presentation? What is the primary focus? The primary focus of this series is upon explicit vector programming. The target audience is C and C++ developers interested in taking better advantage of underlying vector hardware. We'll be introducing some new concepts that can be implemented with new vector features added to OpenMP 4.0. These features are called SIMD-enabled functions, formerly called elemental functions, and Pragma OMP SIMD. Note that all the code examples in this series will be given in C and C++, but the OpenMP constructs are available to Fortran developers as well. I'd like to begin this discussion with a problem statement. The multiplicative effect of large vector widths coupled with the large number of processing cores means tremendous numbers of computational units are available at a hardware level to compute with. But programming languages are limited by their inherent serial nature from putting much of this computational power to good use. So, lots of computational power is available by the hardware, but we have until now had limited software access to it. The solution: extensions to conventional programming languages are needed to tap this power. Multiple methods are available to developers to program using explicit vector programming. We will explore primarily the OpenMP 4.0 approach to explicit vector programming in this series. The goal is to provide language extensions to simplify vector programming, enable developers to extract more performance from SIMD processors in more parts of their application. What is depicted in this graphic is a three-dimensional abstraction. It represents the two-dimensional landscape of parallel computing as it has been evolving over time as a third axis. Time is seen progressing with an upward arrow indicating newer architecture near the top of the diagram. Core counts are represented into the page, and vector widths are indicated by the left to right arrow. What we see is, starting with processors that first supported SIMD capability using 64-bit MMX, such as the Pentium with MMX technology, up until the present, both core counts and vector widths have been increasing over time. The ramification of this is that more computations, governed by the width of the SIMD registers, could be computed per core. For this example, we are focusing on floating point types, but the same argument can be made for integer data types as well. The original 64-bit MMX registers, together with vector instructions, could accommodate simultaneous computation of two integer operations at the same time. Later, SSE and SSE2 vector widths were increased to 128 bits. So SSE allowed 4 32-bit single precision floats to be computed, and then followed SSE2 in the Pentium 4 timeframe, which added more data types, such as allowing two 64-bit doubles or 4 32-bit integers to be computed in addition to other combinations. With processors codenamed Sandy Bridge, vector registers were increased again, this time to 256 bits using YMM registers. Together with new instructions, this provided another doubling of SIMD computational power. For example, Sandy Bridge can process 8 single precision floating point values at one go, or 4 double precision values at the same time. Now, with the advent of Intel Xeon Phi coprocessors using many integrated core architecture, the ZMM registers are 512 bits wide, which can accommodate 16 single precision or 8 double precision floating point operations concurrently. The Intel compiler has long supported the auto-vectorization feature, which could automatically try to vectorize loops where it could, given the serial constraints of the languages. But now, with ever more SIMD resources available per core, and the multiplicative effects of the number of cores available, there is a tremendous need for programming models that extend current languages to allow explicit access to all this computational power. So the observed trend has been for vector widths and core counts to both increase, and their impact can be multiplicative. Intel provides developers with explicit methods to address these trends. So how should a developer think about this explicit vector programming paradigm? The short answer is to think of it in an analogous way to threaded programming as it is done in OpenMP. For several years now, explicit parallel programming was widely embraced by programmers to effectively exploit performance with increasing core counts. Now it's time to also exploit explicit vector programming. With new Intel products spanning graphics processing, traditional CPUs, coprocessors, there is a need for a programming model that a developer can use across any number of platforms and which can take full advantage of the underlying hardware, including multiple cores and increasing vector widths. What we will be describing in this series are explicit vector programming capabilities that are working their way into compilers such as the Intel compiler and GCC and LLVM, and into standards such as OpenMP 4.0. In a nutshell, you can think of explicit vector programming as being to compiler auto-vectorization what OpenMP threaded programming has been to compiler auto-parallelization. Just as a developer would want to take explicit control over the parallelization opportunities in an application using OpenMP rather than relying on auto-parallelization done by a compiler, so a developer would want to take explicit control over the vectorization opportunities using explicit vector methods rather than relying on auto-vectorization. So what are the main components of explicit vector programming? These two components, SIMD-enabled functions, formerly known as elemental functions, and Pragma OMP SIMD. We will be exploring each of these components in greater depth in future videos in this series. So what is the key message? Explore explicit vector programming now to enable the potential performance in your application. Let's explore one of our big performance objectives. The objective is to maximize our use of SIMD hardware per core by using explicit vector programming methods. To understand the objective, it may be helpful to think in terms of vector lanes and to think of instructions as analogous to race cars traveling in these lanes. A vector lane represents the number of concurrent operations that can be computed per core or per thread using SIMD hardware. Each of these graphics represents a single thread. We will explore how to determine the number of vector lanes later in the series. For now, just remember that the later generations of Intel hardware with wider vector registers provide more lanes for instructions to travel, and the developer's choice of the data type also governs the number of lanes available. Consider a loop where a significant amount of time is spent. If this loop in particular is performing in scalar mode, performance is likely suffering compared to where it could be. In this scalar loop, for a single thread of execution, there will typically be a large number of instructions that will be executed prior to the end of the loop. So a lot of instructions for one loop iteration. Let's say in a given loop, at an assembly language level, we require 16 loads, 8 multiplies, 8 additions, and 16 stores, and we also make a couple of function calls that each execute a small number of instructions. Each loop iteration might execute, let's say, 200 instructions at the assembly level. Assume that each instruction takes a single clock tick for simplicity. Then each loop iteration would take 200 clock ticks. The analogy is to think of 200 race cars racing down the loop on a single lane avenue, doing lap after lap until the number of loop iterations is complete. Now let's assume that we ran this code on SSE2 platform and that we had chosen a 32-bit wide data type for the data manipulated in the loop, giving us 4 vector lanes of highway, and that we did our best to vectorize the loop, but we were hindered in fully vectorizing the loop by 2 function calls. This situation is analogous to the same 200 cars traveling down a 4-lane highway, but has spots of road construction which narrows traffic to a single lane for a few miles. This causes traffic congestion and negatively impacts performance. So the 200 cars will likely get through the lap faster than if the route was a single lane for the entire loop, but we still haven't hit a high degree of efficiency. We still have cars jamming up at points within the loop. Now let's consider running the code on an AVX-capable platform, such as a processor codenamed Sandy Bridge or codenamed Ivy Bridge, which have wider vector lanes. Using explicit vector programming techniques, we have successfully vectorized the entire loop, even vectorizing the functions that hindered us previously. This is analogous to a clear stretch of 8-lane highway before us. Now those same 200 instructions can be executed in 25 clock ticks rather than 200 clock ticks as before. It may be helpful to think of this analogy when thinking of vector lanes. There is more performance improvement potential when more vector lanes are used and when they are used fully in each loop iteration, so use all vector lanes if possible. Also remember that these lanes are not threads. Each thread running on a single core has the potential to take advantage of these wide vector lanes. The takeaway here is that we want to achieve the goal, if possible, of maximizing vector lane usage. This series explores how to explicitly target wide vector lane use using C and C++ with OpenMP 4.0 vector specifications. This concludes our first video. Please take a few minutes to watch our next video in the series, Performance Essentials 2, where we begin to explore concepts underlying SIMD.